Hello students, so far we are done with induction motor. Now let us try to understand one of the induction generators, okay, that is Dfig induction generator. Okay, so before going to Dfig induction generator, let us try to understand the operation of motor first. So for motor operation, this is a stator winding, this is a rotor winding. So we are going to supply a 3-phase balanced AC supply to our stator, you know that. Okay, so that will induce a rotating magnetic field in the stator. Okay, I have a stator rotating magnetic field, will induce a stator rotating magnetic field. So at the time of starting, the rotor speed is 0. So this stator rotating magnetic field will cuts with the rotor conductors, that induces a rotor rotating magnetic field. That means okay, there will be a rotating magnetic field in the rotor side also. Okay, the speed of the stator rotating magnetic field is synchronous speed, as well as speed of the rotor rotating magnetic field also synchronous speed. So now our rotor starts rotation, it is speed of nr, okay, in the direction of rotating magnetic field. Okay, so up to this we know, and the difference between our synchronous speed and our rotor speed is called slip speed, and percentage slip is given by ns minus nr by ns. So up to this you know these concepts. Okay, we are supplying the stator is inducing a stator rotating magnetic field, so that links with the rotor conductors, where another rotating magnetic field will be induced, and due to that interaction between the air gap or rotating magnetic field and rotor rotating magnetic field, there will be a rotating force, that is called torque. Okay, due to the torque, our rotor will be experiencing a force that rotates the rotor. Okay, the rotation will be given by nr. Okay, rotor rotation. So the difference between rotor rotating magnetic field and the rotor rotation is slip speed. So up to this we know. Now what we are going to do, and we know that for motor operation, ns is greater than nr. Okay, synchronous speed is greater than our rotor speed. For generator operation, the difference will be nr will be greater than ns. Okay, the rotor speed greater than synchronous speed, then the induction machine is operating as a generator. One more thing, our stator operates at a frequency of supply frequency f, and the rotor current frequency is slip frequency, that is s times f. S is slip here. Okay, you know that, right? Now let us try to understand the torque slip characteristics of our induction generator and induction motor. Okay, so this is the torque slip characteristics of our induction machine. Okay, so here you can see the torque slip characteristics of a motor are between slip equal to 0 to slip equal to 1. So that means this region, in this region our induction motor operates as motoring mode. Okay, that means our rotor speed is less than synchronous speed. That means rotor speed at the time of starting, our rotor speed is 0. So at the time of s equal to 0, our rotor speed will be equal to synchronous speed. So this is not possible in induction motor. So up to this we are trying to get the speed of the induction motor. Okay, the no load speed of the machine will be around this. Okay, so this at this point of torque interaction, okay, if this is my low torque, this will be the operating point of the machine. Okay, so this will be the full load speed of the machine. Okay, so we try to operate the machine at the speed of close to synchronous speed in induction motor. So now when we supply our rotor energy, you know that this is motoring operation. Motoring operation means electrical energy is given to the machine. Okay, machine will deliver mechanical energy. Okay, so electrical energy is nothing but synchronous speed, and mechanical energy is our rotor speed. Okay, let us assume. So in generating mode, when slip equal to negative, that means when slip will be negative, the value of slip will equal to ns minus nr. You know that. Okay, so when this will be negative, when this value will be negative, when the rotor speed is greater than this value. So when 1 minus 2, when as 2 greater than 1, this value will be negative 1. That means whenever our rotor speed is greater than synchronous speed, this slip will become negative. That means in this region our rotor speed is greater than our synchronous speed of the machine. So this is what idea. So in this region our slip will be negative. Okay, so our slip will be negative and the motor will behave like this. This is torque will be negative, slip will be negative, torque will be negative. So this region is called generating region of our induction motor. So induction motor can also be used as a generator for wind generations. Okay, I will going to explain later. So this is generating region of operation. At that time our rotor speed is greater than synchronous speed. As it is generating mode, we supply our mechanical energy to the machine. Okay, so as we supply mechanical energy to the generator, and it will deliver our electrical energy. That means nr is greater here compared to our synchronous speed. That means this is greater, synchronous speed is greater in motor operation, and rotor speed is greater in generator operation. So this is about torque slip characteristics of motor and generator of our induction machine. Okay, and you know that this is a braking operation. Okay, as slip greater than equal to 1, we try to block the rotor of the machine. Okay, when slip greater than equal to 1, that means whenever our speed of the rotor equal to 0. Okay, s equal to ns minus nr by ns. Okay, whenever nr equal to 0, our slip will be 1. Okay, this is at starting condition. Okay, if slip is greater than 1, that will come under braking condition. Okay, so this is about torque slip characteristics of our induction machine. Now let us try to understand our Dfig induction generator. So here is the black diagram to understand the doubly fed induction generator. Okay, as our doubly fed induction generator is a variable speed generator. Okay, it is a variable speed generator because, so you have already seen the induction generator. So there are two types of induction generator. One is grid connected induction generator, another is isolated induction generator. Okay, in grid connected induction generator, our grid will supply the reactive power required by the induction motor. In isolated induction generator, there is a capacitor bank placed on the stator circuit, connected to the stator circuit, that supply the reactive power to our rotor, our induction motor as well as load. You have already seen the videos, right? So now let us try to understand the doubly fed induction generator. Okay, so here we need to have our rotor speed greater than synchronous speed to have our induction motor operate as induction generator. Okay, but in case of our doubly fed induction generator, it is possible to run the machine as generator even our rotor speed is less than synchronous speed. So that is the application of our doubly fed induction generator. That is, it is a variable speed generator. That means our machine will operate as a generator even the rotor speed is less than synchronous speed. Okay, even the rotor speed is less than synchronous speed, our machine will operate as generator, and it will operate as generator even our rotor speed is greater than synchronous speed. So when our rotor speed is less than synchronous speed, this mode of operation is called subsynchronous operation. Subsynchronous generation or operation. Okay, this is subsynchronous generation. So whenever our rotor speed is greater than synchronous speed, this operation is called super synchronous operation. Okay, super synchronous generation. Okay, whenever our rotor speed of doubly fed induction generator is less than synchronous speed, that mode is called subsynchronous generation mode. That means our machine will generate the electricity even the rotor speed is less than synchronous speed. Okay, and it is, if rotor speed is greater than synchronous speed, that mode of operation is called super synchronous generation. Okay, so let us try to understand what is a doubly fed induction generator. So these are the application. One is subsynchronous, another is super synchronous, and it is a variable speed generator. Okay, so generally what is the application of our doubly fed induction generator is, so you know that windmills, right? Wind power generation. Okay, let us assume it is a windmill generator. Okay, so you will be having a gust of wind. Okay, then our windmill rotates. Okay, and this is connected to a generator, that is our doubly fed induction generator. Okay, and you cannot define the speed of our wind so that it will deliver constant rotation to our generator. Okay, so for a synchronous generator, you need to give a constant speed to the generator as mechanical input. Okay, but in case of our doubly fed induction generator, our doubly fed induction generator is a variable speed generator. That means it can generate the power even in the subsynchronous mode of operation, that is when our rotor speed is less than synchronous speed, or in the super synchronous mode of operation when our rotor speed is greater than synchronous speed. Okay, so we don't need to we don't need to rotate the rotor of the machine to generate the power at a constant speed. We don't need to rotate the rotor at a constant speed in Dfig. So that is the best advantage of our Dfig. That means we don't know the speed of wind, right? It may be at a speed of 1500 rpm at one time or 300 rpm at another time. Okay, so we don't define the speed of wind, right? So at any speed of our windmill, we need to deliver our electrical energy to the grid. Okay, so in order to have the advantage of variable speed generation, we are going to place our doubly fed induction generator in windmills. Okay, so as speed of windmills is not constant, we are going to supply a variable speed to our doubly fed induction generator, which generates electricity at any speed of our wind generator. Okay, so this is the application of our Dfig. So now let us see how our Dfig is operating. Okay, so as it is induction generator, it needs some magnetizing current I mu. Okay, its rotor has to be excited, rotor excitation. Okay, rotor magnetization I can say. As it is induction generator, rotor or winding should be magnetized. Okay, so we need to supply some reactive power or some supply to our rotor so that our machine will operate without any problem. Okay, so how it is happening now? Okay, in isolated induction generator, your generator has been supplied with a delta connected capacitor bank. You already seen that, right? It is a delta connected capacitor bank. Okay, you have already seen this, I think. So this is a delta connected capacitor bank, right? This capacitor bank will supply reactive power to load as well as your induction generator. So this is isolated machine. In grid connected induction generator, your reactive power will be supplied by grid itself. But in case of our doubly fed induction generator, here what is happening here? So we are going to rotate the rotor of our doubly fed induction generator. Because it is a generator, we need to supply our mechanical energy to the rotor. Okay, so the mechanical energy is coming from the windmill. Okay, so this is mechanical energy I am giving to the rotor, and we need to excite the rotor circuit. We need to magnetize the rotor circuit so that the operation will be possible. Okay, so I am going to give, and we need to supply to the rotor with a frequency of supply frequency. You already know that. Sorry, slip frequency. Okay, the frequency of excitation to the rotor should be of slip frequency. Okay, and here what is happening here, this is a grid, this line is a grid. Okay, so we are going to take a 3-phase power from the grid, and that is being converted from AC to DC here, and again it is converted to DC to AC. So why it is happening? Because our supply frequency is 50 Hz. Okay, and we need some slip frequency to our rotor, so we have to reduce that frequency to around 2 to 5 Hz. Okay, that is only possible in DC link conversion. Okay, there is a DC link converter. Okay, we have to change the supply frequency which is of 50 Hz to around 2 to 5 Hz of rotor frequency, then only we can supply the energy to the rotor. Okay, we need to supply the energy to the rotor with a slip frequency. That is possible if we can convert the supply frequency to our slip frequency. So that is being converted from AC 3-phase AC to DC, then again it is again converted to AC by using our DC link converter. Okay, so this is having a frequency of slip frequency, then that will be supplied to our rotor of our Dfig, double fed induction generator. Thus we have the rotation in the rotor and we have excitation in the rotor. This excitation will link with the stator conductors that will induce EMF. Okay, that EMF is fed to our grid. This is to grid. Okay, so we are taking some power from the grid. Let us assume this is PR is a rotor input power and PG is a grid power. So this is my mechanical power. So these are the 3 powers. Okay, so what are the inputs here? Here our inputs are our prime mover input, which is PM, and our rotor input PR. What is the output here? It is PG. Okay, so there are 2 modes of operation in Dfig. One is subsynchronous and another is supersynchronous. Okay, so let us understand one by one. So I hope you understand the operation, right? We are going to supply our rotor of the induction generator using a DC link converter, which converts supply frequency to slip frequency, and it generates required reactive power by the rotor of the induction generator, and that magnetizes the rotor of the induction generator, and it is being rotated by our windmill. It cuts our rotating magnetic field will link with the stator stationary conductors that will generate EMF. Okay, that voltage will be supplied to grid again. Okay, so let us try to understand our subsynchronous operation of Dfig. So before going to understand our subsynchronous mode of generation, let us try to understand our power flow again. Okay, so you know that there is a rotor power input is to rotor copper loss is to our gas mechanical power developed in the rotor is given by the ratio of 1 is to S is to 1 minus. You already know that, right? So let us try to obtain our gas mechanical power output with respect to rotor input, that is PGM by P rotor input equal to 1 minus S into 1 minus S by 1. So that is our gas mechanical power equal to 1 minus S times our rotor input. So we know that what is rotor input? Okay, rotor input is nothing but rotor input nothing but stator input minus stator losses is nothing but our rotor input. Okay, after cutting our stator losses from stator input, we are going to deliver our rotor power to rotor. Okay, after cutting stator losses from stator input, then only our power will be supplied to rotor. That is power to the rotor equal to power from stator minus losses in the stator. Okay, power from stator minus loss in the stator, then only power will be flow to our rotor. Okay, rotor power input is nothing but stator power input minus stator losses. And here in the generation mode, okay, so this is my shaft power rotated by windmill. This is my shaft power PSH. Okay, after mechanical losses from shaft to our rotor, so there will be some mechanical losses. So after substituting mechanical losses from shaft power, then only we will be getting our gross mechanical power in the rotor in generating operation. Okay, so our gross mechanical power is nothing but shaft power which is supplied by windmill in generating mode minus our rotor losses, that is mechanical losses. After subtracting mechanical losses, we will be getting some gross mechanical power from the shaft. Okay, so that is about generating operation, right? So let us in this operation, if this is motor, okay, if this is motor, we are supplying the stator input. So there after subtracting stator losses, we will be getting rotor input. For generator, what will be the expression? We are giving supply to stator. We are giving power from rotor to stator. That means rotor input will be sum of stator input plus stator losses. Okay, this is the idea. I hope you understand. So if it is a motor, we are giving the supply to the stator. So after subtracting stator losses, the power will be passed to rotor. But in case of generator, we are substituting we are supplying the power from rotor to stator. So rotor power will be equal to stator power plus stator losses. Okay, so let us try to neglect these losses so that there will be no confusion. That means I am going to make our rotor input equal to our stator input. Okay, I am neglecting these losses here, and our gas mechanical power output equal to our shunt power. So for simplicity, I am going to take our shaft power is nothing but gas mechanical power, and our rotor input is nothing but our stator input. Okay, so I am neglecting the losses here. Okay, now let us try to understand subsynchronous generation. Okay, here for subsynchronous generation, we know that our rotor speed is less than synchronous speed. That means slip is nothing but ns minus nr. Okay, as rotor speed is less compared to synchronous speed, our slip will be positive. Okay, so let me consider a slip. For example, it is 0.2 for under full load. Okay, this is the range of slip for full load, right? So now let us try to understand. So under subsynchronous generation, what is happening here is, as the rotor is less speed compared to synchronous speed, our rotor cannot generate any power in the rotor circuit. That's why it requires some reactive power from the grid. That is, PR is needed by the rotor. That means PR is going into the rotor circuit here. Okay, and we are giving mechanical power from our windmill here. Okay, that is, let me write here. So what is the gross mechanical power output here? That is 1 minus times our rotor input, or rotor input, right, which is nothing but our stator. Let us assume stator supply. Okay, I'm going to substitute rotor input. I have replaced the rotor input with the stator power. Okay, so let us assume the stator power we are supplying to the grid as 100 watts. I am going to supply 100 watts of power to the grid in subsynchronous generating mode. Okay, let us assume I am going to supply 100 watts. This is fixed value. Okay, I am going to supply 100 watts to the grid. Now let us see what is the value of PGM here. PGM will, which is nothing but gross mechanical power developed in the rotor, which is equal to 1 minus, what is the slip here? 0.2. Okay, and P supply is 100 watts. So what is its value? That is around 80 watts. Okay, our gross mechanical power given to the rotor of our induction machine is 80 watts. Okay, but we are supplying 100 watts to the stator. That means how it is possible? This is the only input here. Okay, this is nothing but input, right? We are giving the mechanical energy, that is PGM is 80 watts here, but our machine is supplying 100 watts from the stator. This is input, this is output. They are not equal. That means our machine will draw a rotor power of 20 watts here. Okay, the machine will draw a rotor power of 20 watts. That means our this 20 plus 80 will become our our supply power. That means we are adding our gross mechanical power plus our rotor power, then only it will be substituted to our stator. Okay, that means the net power we are generating is nothing but this 80 watts only, because we are giving 100 watts to the grid and we are taking 20 watts. What is the net? 100 minus 20. That means we are supplying only 80 watts to the grid. That is the idea here. Okay, I hope you understand, right? So we are giving 100 watts of supply to the grid, but the mechanical supply we are giving to the rotor is 80 watts only. That means our machine will take 20 watts from the grid as a rotor input, that will sum up to our 100 watts. That means we are supplying only 80 watts to the grid. Net supply to the grid is 80 watts. That means we are taking 20 watts from the rotor circuit. Okay, we are giving 80 watts of mechanical energy here. Okay, this is 80 watts. Mechanical energy is 80 watts. Okay, the power flow into the rotor is 80 watts and power flow out of the stator is 100 watts. That is only possible if I supply a rotor power of 20 watts. Okay, these two will add up and 100 watts will be supplied to the stator. That means in this case, what is happening? Our mechanical power and rotor power are adding up and giving stator power to the grid. Okay, so that is the idea here. Now let us try to understand our super synchronous mode. Super synchronous mode. So what is super synchronous here? Whenever our rotor speed is greater than synchronous speed, that means our slip will become positive. Sorry, slip will become negative. So let us take the same example here. Slip is negative here minus 0.2. Okay, our power supply to the stator is, let us consider it PG equal to 100 watts. Sorry, 100 watts. Let us say it is 100 watts. Okay, so PGM will become our gross mechanical power developed in the rotor equal to 1 minus S times our PG, that is nothing but 100. Okay, that is 1 minus, what is the S value? That is 0.2 into 100. That will become 1.2 into 100, that equal to 120 watts here. Okay, so here you can see that our PGM gross mechanical power developed in the rotor is 120 watts and it is supplying the stator 100 watts. Okay, the power given to the rotor is 120 watts, but it is supplying stator 100 watts only. That means the extra 20 watts, where it is going? Here in super synchronous mode, this extra 20 watts will go through the rotor circuit to the grid. That means our PR will be here negative 20 watts. Okay, that means our power from the rotor will be towards grid here. This is 20 watts. Okay, the power from the shaft is 120 watts here. Okay, this is the power flow and this is 100 watts fixed. Okay, the power flow into the rotor is 120 watts. Okay, and it is giving grid as 100 watts and from the rotor circuit is giving to the grid as 20 watts. Okay, in this mode our PGM is sum of our power generated plus our rotor power. Okay, in subsynchronous mode, our PGM and our rotor power added up to our generated power. Okay, so this is the idea here. Okay, here our gross mechanical power output is supplying stator and our rotor. Okay, this is our generated power and this is rotor power. Okay, in case of subsynchronous mode, these two will added to make 100 watts. In supersynchronous mode, this is substituting, this is supplying 100 watts and our stator power and rotor power. So that is the idea. In supersynchronous mode, our rotor will also deliver some power to the grid. So that is the idea. Now let us try to draw one graph so that you can understand the things. So here, okay, in subsynchronous mode, what is happening? So this is subsynchronous, this is supersynchronous. Okay, here under at subsynchronous mode, our PM, PGM are nothing but PGM and PR are like this. Okay, so in supersynchronous mode, we are delivering, this is fixed PG here. P generated is fixed value, okay, which is of 100 in the example, but that is some in subsynchronous mode, our PGM plus PR equal to PG here. Okay, this is the mode separation. Okay, below this, that is subsynchronous mode, above this point, that is supersynchronous. So in subsynchronous mode, what is happening? The sum of PGM and PR, the sum of this PGM and PR will contribute our PG. Okay, in supersynchronous mode, what is happening? Our PGM, okay, this is the value of PGM. So here it is PR, here it is PG. Our PGM is substituting our generating power in the stator and our rotor power. Okay, this is supersynchronous mode of operation. This is subsynchronous mode of operation. In subsynchronous, our gross mechanical power and rotor power contribute to our stator power generated. When supersynchronous mode, our generated power and rotor power with the sum of these two will become our gross mechanical power. Okay, I hope you understand, right? Yeah, at this point it is slip equal 0. Okay, it is positive slip, it is negative slip. Okay, so under subsynchronous mode, the sum of gross mechanical power and rotor power contribute to our generated power. In supersynchronous mode, the sum of our rotor power and generated power are equal to our PGM. Okay, this sum is nothing but PGM here. So this is about Dfig induction generator. It is a variable speed generator. Okay, you will see one important generator, that is synchronous generator, which is having a constant speed generator. In the 5th unit, you will come to see here. Okay, that is the rotor of the synchronous generator has to be rotated at a constant speed, that is synchronous speed. So that is used in thermal power plant and hydel power plant. But Dfig application of Dfig is wind power generation. Because wind power is not constant all the time. The speed of the wind varies time to time. So even if you have a variable speed, then you can generate the power. That is the idea of Dfig. Okay, I hope you understand, right? Thank you.